Hi guys, let's answer the questions posed at the end of the binomial probability follow-up video. Here are the three questions that I asked you guys at the end of the binomial probability follow-up video. First, what's the probability of getting a 6 in 10 rolls of a fair die? Remember, I asked you guys to think about how could a die with 6 outcomes be modeled with binomial probability. But then I also thought that you'd probably be able to figure that out, and I hope you did. We're going to be coming to that. Second question. Using a fair coin, what's the probability of 3 heads in 6 rolls? And then finally, using an unfair coin, and this is the same coin I've been using throughout this series of videos. Let's imagine a coin, and I just pulled this out of thin air. I just said, let's suppose there's a funny coin out there where the probability of heads is 2/3. So it's an unfair coin. And I did this for a reason. I actually had a question. Why did you do that? And the reason for that is that when talking about binomial probability, I want to be able to differentiate the various parts. Remember the formula. Part of the formula is about successes, and part of the formula is about failures. And if everything has the same probability, it's hard to differentiate them. So, and it's also kind of fun to do it this way. So, third question. Using an unfair coin, probability of heads equaling 2/3, what's the probability that you'd receive at least 2 heads in 7 trials? That is 7 flips. So we're going to go ahead and explore those. I actually think I'm going to do the second question first because it's the simplest. Okay, so we're going to talk about the second question first. What is the probability that we're going to flip a fair coin 6 times and get 3 heads? Now remember, a fair coin, when we say that, we mean a coin where the probability of heads is equal to 1/2, and that means the probability of heads complement is 1 minus 1/2, which is also 1/2. So what we're proposing is that we're going to flip the coin 3 times and get 3 heads. You guys, if you've seen the previous videos, you know what the formula for binomial probability is. It's 6, choose 3, 6 trials, and we're looking for 3 successes. Let's define heads as our successes in this case. Then the probability of success to the power of how many successes there are, that's times, that's multiplying, times the probability of failure just for form. I'm writing 1 minus the probability of success. We all know what that is. Remember, the probability of failure is the number of trials minus the number of successes. I could have easily just put a 3 there, but let's be clear and explain it where we can. So this is another illustration for why I like to mix it up a little bit and use different probabilities. It's really tempting to say, hey, I see that this is 1/2 to the 3rd power times 1/2 to the 3rd power. Let's just make it 1/2 to the 6th power, and that's a valid shortening when you're really comfortable with this and you really know what you're doing. If you're still trying to learn it, taking shortcuts that obscure what's actually going on isn't really a good idea. So if you want to do that, keep your eye on the ball really closely. Remember that that is just a contraction of this, and it's a convenience made possible by the fact that our probabilities are symmetrical, 1/2 and 1/2, both for success and failure. Okay, well, we're going to come back to that. Let me make some space. The first thing we ought to do is the combinatoric segment, so I'm going to do that first. Let's do that. That's going to be 6 choose 3, or 6 factorial, divided by 3 factorial, multiplying 6 minus 3 factorial. Here I will take a shortcut because I'm sure you guys are fine with that. And 6 factorial is 6 times 5 times 4 times 3 factorial, 3 times 2 times 1. And we're going to put that over 3 factorial times 3 factorial. That's what we have right here. So that's a straight up quick simplification. We can cancel those, and we have 6 times 5 times 4. If you already see what's going to happen, that's awesome. Being really accurate with math is taking a deep breath sometimes and going through the motions, because sometimes you'll be surprised. Anyway, I see that we have 3 times 2 on the bottom, that's part of 3 factorial. I'm going to cancel that versus the 6 on the top. And this ends up being 5 times 4 over 1. I'll take another shortcut. Yes, I'm a hypocrite. Well, that's the 20. Next part of this will be 1/2 to the 3rd power times 1/2 to the 3rd power. I'm not writing 1/2 to the 6th power this time. Let's do it right. I won't take the shortcut. Remember, we're going to be taking the combinatoric expression of 20 and multiplying these expressions by that. So what we have is 20 times 1/8 times 1/8. I'll leave it for you guys to figure that out. That's going to be, what does that come to? 20 over 64, which is 5/16, and that's going to come to about 0.3125. Great. So that's the second question, and I think the easiest. Let's go ahead and do the other ones now. I'll start with the first one. I'll go next to the first one. Okay, next one. The next question was, using a die, one dice, a die, what's the probability of getting a 6 in 10 rolls, 10 trials? The 6 occurring 4 times. So we're defining, this takes a little bit more thought than last time, and the probabilities won't be symmetrical. But here's how we're going to think about it. Well, we're going to use the binomial theorem because we're really seeking a 6. So we're going to define the 6 as our success. So the probability of a 6 on a fair die, and it was defined as a fair die, is 1/6. Why? Because all the probabilities on the dice, on the die, are the same, and there's 6 outcomes possible, the 1, the 2, the 3, 4, 5, and 6. And the 6 is 1 out of those 6. So the probability of a 6 is 1/6. That makes the probability of failure, remember 6 is just success, and I'm going to start writing it like this. Failure is the complement of 6, and that's going to be 1 minus the probability of success, and that's the probability of failure, 5/6. Now we're going to roll this dice 10 times, and I want this success to occur 4 times. So we're going to start out with 10 trials and 4 successes, and that's a good way to think about the combinatoric expression that we started with at the beginning, times the probability of success to the power of how many times we expect it, times the probability of failure. Let me take a shortcut here, and I'll go straight to 5/6 instead of 1 minus 5/6. To the power of how many times we expect failure. If we have 4 successes in 10 trials, 10 rolls, then I expect 10 minus 4 failures. So that's our expression. Okay, so let's go ahead and figure that out. The first thing we should do, I think, is to do the combinatoric expression. So that's going to be, by the way, again, I think I mentioned this earlier, but let's not miss something. This number matches that exponent. The number of trials matches the sum of the 2 exponents. That's kind of a good thing to realize and to notice and to point out to yourself, isn't it? If those things aren't true, these 2 numbers adding up equaling that, and these 2 numbers matching, if those things aren't true, then it's not set up correctly. You need to have your probabilities correct too, but that's just one self-check you can do. So we're going to do 10 choose 4. That's going to be 10 factorial over 4 factorial, 10 minus 4 factorial. Again, I hope you don't mind that I've taken a shortcut there. So 10 factorial is actually 10 times 9 times 8 times 7 times 6 factorial. Unlike last time, I'm not even going to write that. We're going to put that over 4 factorial. 4 factorial is 4 times 3 times 2 times 1. Let's see what cancellation we can do. Well, I know that the 8 can cancel versus that 4 and the 2 because they're all multiplying. And the 3 can go away versus that 9, leaving a 3 behind. So what we have is 10 times 3 times 7, that's what's left on the top, over 1. And that's going to be 210. Check it out. Do it on your own and make sure I'm correct. So our combinatoric expression yields 210. I'm going to make us some space. And then we have, so that's 210. 210, that's multiplying 1/6 to the 4th power. Try that out. Here's what I suggest. Depending on the phone you have, and sometimes it's a really good phone, will make this mistake. If you take an exponent, especially something that's a never-ending decimal like 1/6, and you do complex things with it, stuff that's hard for your calculator to do, like taking roots or powers or logs and so on, you'll find that they're not always correct. They're not always correct. So do it with a calculator. That's what I did. And you'll probably get something more accurate. Now I went ahead and I rounded and truncated these values anyway. But just a word to the wise, if you're looking for accuracy, sometimes the phone won't give it to you. I'm going to go ahead and fill in the value that I got for that right now, because I talked enough. Let's go ahead and get right to the point. So 1/6 to the 4th power, I got 1,000,000. I'm going to throw in some digits, 771,605. And then for 5/6 to the 6th power, I got, let's multiply. Sometimes I'll put a dot, but this time I'll be real extra clear and put a asterisk, meaning multiplication. 0.3348979. It's also always possible that I'm going to be making a mistake. So, go ahead and make sure that I've done it correctly, and comment or message me or something if you think you should offer a correction. Okay, so this is where we should be right now. By the way, a word to the wise. Here's a good technique. When you end a sequence like this with something difficult for us to do, or for the calculator to do, with a lot of decimals, like 5/6, you've got 0.3348979 sitting in the display of your calculator. So don't clear it. Just immediately hit multiply, and you can multiply it by this. And then by that, finally, if you're not comfortable using complex syntax, entering a long string into your calculator all at once. I don't always like to do that because I find that it's easy for me to lose my place. So I'll do these things separately like I have in front of you right now. But once you have one of the values sitting in the display, don't clear it, utilize it, and then you can multiply the string, the rest of the elements of the string, if you need to. I multiplied this, and I got 0.0542658. So that's what I got. So about 5.4%. Does that seem intuitively correct for you, that you'd roll a die 10 times and get exactly 4 6s? Well, remember, the 6 is relatively unlikely. It's 1/6. And we're specifying something kind of specific. I didn't say up to 4 6s. I didn't say at least 4 6s, specifically 4 6s. So you've got, in terms of events, a relatively small target. So for me, intuitively, that makes sense, about 5.4%. But go ahead and do it on your own and see if you also agree. Let's go on to the third one. Okay, so third problem. Let's take a look at what happens if we have an unfair coin where the probability of heads is equal to 2/3. It's a coin we've used before. And we are in 7 flips of that coin. We're going to look at the probability that the number of successes would be equal to or greater than 2. Okay, so at least 2 successes. So that means that equal to or greater than 2, that means that we're proposing the probability that we would get 2, 3, 4, 5, and so on, successes all the way up to 7. What's the sum probability of that? And we could do it that way. You can be very successful doing the problem that way. It's a lot of work. You have to figure out the probability of 2 successes, and then 3, and then 4, and 5, and 6, and 7. And add all of those probabilities together. That's a fine way to do the problem, but it's a lot of work. So what we're going to do is use a different strategy. This is a strategy I refer to frequently. What we're going to do is examine the sample space for the number of successes, in this case, remember it means heads, the number of heads that we can get in 7 flips. So it's possible to get only 1 head or 0 heads. Those aren't parts of the problem that we want, though. But we're going to keep in mind that the entire sum of the probabilities in a sample space must be 1. So what we're going to do is identify the part of the sample space where we analyze the sample space in terms of the number of heads that we might get. We're going to identify the part of the sample space that we do not want, and we're going to subtract that from 1 to get our answer. So I'm going to take the probability of 0 heads and the probability of 1 head, and we're going to add those together and subtract that sum from 1 to be left with the part of the sample space that we do want. That's this part. Let's go ahead and proceed with that. We're going to do that. Let me make some space. Okay, so 1 minus the probability, let's start with the probability of 0. So I'm just going to plug this right into the binomial probability theorem formula, and that's going to be 7 trials choose 0 successes times the probability of success, which is 2/3, let's make a multiplication right there, to the power of the number of successes we're proposing right now for the moment, and multiply that by the probability of failure to the power of the remaining trials. So the failure probability, remember, is going to be 1/3. And we have 0 successes, so that means all 7 trials result in failure. So what we're going to need to do is figure out what this is and add that to the probability of 1 success and eventually subtract it from 1. 7 choose 0. How many ways are there to have 0 successes among 7 trials? Well, it's going to be 1. Remember, it's the shortcut you can use. Any number choose 0 is going to be 1, so that's 1. We have 2/3 to the 0 power. Taking 2/3 to the 0 power is also 1. We're going to multiply that by 1/3 to the 7th power. So that is going to give us 0.000457247. So we're going to keep that in mind. Let me make some space. We're going to add that in. We're going to record that. 457247, and we're going to add that to the probability of 1 success. Let's figure out what that is. And I'm going to set it up. Remember that setup is the big thing with this. So you got to make sure you set it up correctly. So we have 7 trials now and 1 success that we're calculating. 7 choose 1 times the probability of success to the power of the number of successes we have. We're going to multiply that by the probability of failure to the power of the number of failures. If we have 1 success in 7 trials, that means the remaining trials, 6, are failures. So we're going to calculate that out. I think you're at the point where you can probably do that on your own. That's going to give us 0.006401463. Let's add that in. So that's going to be 0.0064, that's a 0, 6401463. And that in schematic form is our calculation. Go ahead and do that on your own. I'm actually gonna take one more step and then give the answer. The sum of those two numbers is 0.068 0.5871, and subtracting that from 1 gives us 0.9931429. Does that suit our intuition? Is the probability of at least 2 successes, at least 2 heads, in 7 flips of this coin, is the probability 99.314%. And that does suit our intuition. This is a coin that we're proposing has a heavily skewed probability towards heads. It's got a 2/3 probability of having a heads. And so we would expect an abundance of successes with this coin. In 7 flips, the probability of getting at least 2 successes is 0.9931429. Go ahead and do that on your own. Make sure I haven't made a mistake. You can go ahead and comment me if I did, or if you have a question, that's even better. Go ahead and send it along. Thanks a lot.